On Thursday instead? I got to turn off the camera to say this, but I think I'm okay with that. So, right. And you probably have a lot of other assignments to catch up on. I'm all about that. Say again?
I also want to go trick-or-treating.
You want to go trick-or-treating? What day is that? Tuesday?
The 3rd. So it's the day before the homework's due.
It's the Monday before. Oh,
Yeah.
by all means, we'll have to delay the homework. Okay. You just needed to ask the right question, Jody.
Thank you.
Okay, so we'll have it due Thursday. All right. Okay, good. Okay, so I'm going to send out a Canvas message to that effect to make it official, and also to make sure that Alicia gets that, because I've been having trouble getting my videos on the internet. So, that's a lot of wasted video right there. All right. I'm going to put some equations over here. N of I, J, K over N of J, K equals G, I, J, K over U of J, K, T times the exponent of minus chi I, J, K over K, T. Everybody hopefully knows what I mean when I say those equations. You really need to get familiar with what this means. This is species K in ionization stage J. This is the same species K in the same ionization stage J, but with the electron or in an excited state I. Okay. So this is what fraction are in excitation stage I for a given species in a given ionization.
Like what fraction of neutral atoms are in an excited state?
Correct, like for hydrogen, right? Of the neutral hydrogens, which fraction are in the first excited state, or are in the ground state, or are in the third state? Okay. Bless you. So you can see that it depends upon the statistical weight of the upper excited state, because that gives you a number of branching ratios to get up there, which increases this ratio. You have the partition function, which gives you basically the weight for all the possible states, and you're normalizing that because this is the density of all possible excitation states. So, and then this is itself the exponential weight for the energy to get up to excited state I. Right. And then we have Ni prime of Jk over Nij, where I prime is greater than I, and that was equal to G I prime Jk over G I Jk exponent of, I hate it when I draw those brackets lame, minus chi I prime Jk minus chi I Jk over Kt. So I'm not putting dots on the i's so that the prime is more clear to you. Okay, now if I is equal to 1 here, then we get the simple relationship of Nij over N1 Jk. This is the ground state. In other words, what's the number density of excited states I relative to the number in the ground state for species Jk? This is G I Jk over G of 1 Jk exponent of. Now you only see one ionization potential show up here because basically you're taking this equation and you're replacing this I with 1. But when the I is 1, it's the ground state. What is the value of that, ladies and gentlemen? Sorry?
0.
0. Okay. So the homework problem, number 2, asked you to exercise these equations. Okay? Do we have any questions about these equations? What are the assumptions that have gone into this equation, these equations? Assumption number 1.
Thermal equilibrium.
Thermal equilibrium, meaning everything, thank you, I can't spell when I'm at the board. Every energy or pressure can be determined by one special macro variable, and that is the temperature. Okay? The radiation field, the number density of photons at each frequency, depends only on the temperature. The number density of the particles and all of their excitation states and all of their ionization states, and the electron density, velocity distribution, and the kinetic energy distribution of all the particles and all their ionization states, blah, blah, blah. It's defined only by the temperature. You can solve every one of those as a function of a single temperature. They all can be defined by that temperature. There are departures from that, though. Later on, we're going to talk about something called local thermal equilibrium. It's an approximation. What's the next one? Detailed balancing. This basically means T for all, and what does this mean? No matter what you're talking about, the rate up equals the rate down, or the rate in equals the rate out. Okay? Whether you're talking about ionization from photoionization, or recombination of an electron, or collisional ionization, or collisional recombination, 3-body recombination, or photoexcitation, or collisional excitation, or collisional de-excitation, and stimulated emission, in other words, stimulated de-excitation from the photon. When you take all of those, they are all balanced. Their rates are balanced. In that way, you get equilibrium numbers that are unchanging. And those equilibrium numbers end up depending upon T and, of course, N, the total N and pressure that we're going to find out. See, notice that these only give you ratios of densities. Okay? What the final conditions of the gas will depend upon what the pressure on the gas is and what the number densities are. That comes from, say, if you're in an atmosphere, it comes from the mass of the star, and it comes from the height up you are in the star and what the hydrodynamic equilibrium is doing. That will dictate your pressure and your density. But all these ratios depend upon one and one thing only: thermal equilibrium, temperature.
If we didn't assume detailed balancing, how would those equations change? Would the statistical weight be different?
These completely break down. No, they just completely break down. They don't apply.
Okay.
And all of a sudden now you have to actually get into calculating the rates for everything and then writing down the balancing equations for the densities and solving them. Usually it's a very nasty nonlinear matrix of problem. Super duper
Because
intense.
like every transition has certain weights. And
Yep. Cross sections, you have to put number densities, cross sections, and you ultimately want to solve for all those number densities. Okay. Now let's talk about the Saha. Can I erase this now? Little review. Now, let's consider the sheer joy I have that I found a marker not destroyed by John. Okay. That little segment's going to go viral for all astronomy majors. Okay. I really am not too interested in talking about this derivation in detail because it's really kind of involved. But what I want you to understand is that it depends upon statistical weights again. So what we do is we start with the Boltzmann equation, N1 in state J plus 1K in the ground state over N ground state JK. All right, this is a 1. All right. Okay. If we just write the Boltzmann equation and account for the fact that this is over some velocity range, we get the electron statistical weight in the gas divided by the statistical weight of the ground state for ion JK times the exponent of minus h nu kt. Now, I've got the derivation much more fundamental in my notes that are at the bottom of that little segment on the web page, the typewritten notes, if you really want to see how it's derived.
Sorry, is that a 1 or an I?
That's a 1.
It's a 1. Up at the top too.
Yes, all of these are 1s.
Those are ones, okay.
Right there. All right. So basically what we're saying is now we've got a situation where you've got some ion in the ground state, JK, and some ion in J plus 1K. So what the difference is that is this has one less electron on it. Okay, so you're removing an electron. Well, let me put it, no, this is wrong. Okay. If you remove an electron, you go this way. Right? When you move the electron, you go to the high ionization state. On the other hand, if you take n of J plus 1 and you have an electron come in, okay, you will emit a photon and get NJK. All right, so let's get this right here. Right. Okay. This process is photoionization. And this process is recombination. Photorecombination, if you will. Okay. We're just going to assume that these two are in the ground state, just for now. It's not that important. It's not important. Okay. So, to get for NJK, the balance is given by the reverse of these two processes. You have the electron pool, okay, recombining with the J plus 1 ion. It emits a photon and becomes a lower ion, J plus 1 to J. Okay. This has one more electron around it than that does. On the other hand, you have the other process where a photon will come in and eject the electron and now put you into a J plus 1 ionization stage. Okay? What we're talking about is the ratio of these two adjacent ionization stages. Okay? That's weird. So here, J plus 1, this depends upon the incoming electron, doesn't it? the incoming electron is going to have some velocity v. Okay? It's going to have some velocity between v and v plus dv. All right? And the cross section for the probability of it is going to depend upon that velocity range. Okay? And the photon's going to end up having some energy h nu. Okay? So if you account for the velocity range that the electron can have, you have basically a statistical weight in the free gas at that velocity between the velocity v and v plus dv. And then for the denominator, you have the lower ionization stage density and the statistical weight for the state that the electron is in there for species JK. And then you have the balance with the photon field through the Boltzmann factor. Okay. I'm not going to go through it, but what is the statistical weight of an electron in a free gas? Okay. All right. It talks about it here. It's basically a phase space argument, and you get 8 pi. If you want to go through this, you can read some books on it. 1 over the electron density, that's very important, times the mass of the electron cubed times velocity squared in the range dv. So now you have the relationship for this term up here, and you see that it depends upon the inverse of the electron density. So the rate, the balance of these two, this is the point, the balance of these two are going to depend upon, through the statistical weight of the free electron, they're going to depend upon the inverse of the electron density. Okay? And the temperature, because here's T, and guess what? The velocity is a function of T. Okay. All right.
So the greater the electron density,
The smaller the statistical weight, and the lower this ratio is. And the real reason for that is because the higher the electron density, the faster is the rate of recombination. The higher the electron density, the faster as this rate is, the more you balance things toward here. So I like to try and teach physics intuitively, so I'm glad you asked a question like that. Okay. Anyway, if you then account for what the photon frequency is, that is h nu is equal to chi of the ionization for JK plus the kinetic energy of the electron. Okay. So basically, what is the frequency of the photon, the kinetic energy, and the potential well? Remember we had that discussion before? That basically when you knock an electron out, first you have to knock it out of the potential well, and then the remainder is the kinetic energy. So if you look at that, the kinetic energy is the frequency of the energy of the photon minus the potential well gives you the kinetic energy. That's conservation of energy.
Is that capital I?
That's a capital I for ionization. So I am introducing a term here. People do this different ways, but if you remember way back when I defined terms, I said chi ijk is the excitation energy. But now we're defining chi I JK, and this is the ionization energy, which for a ground state, hydrogen is 13.598 eV. Okay. So now you have to know the ionization potential. Now, because of time, I kind of skipped over those. Let me see if I got here. Oh no, I've got them here in the page, so never mind, we'll get to them. All right. All right, so I'm not going to go through the derivation now, but I'm going to show you. If you plug in these two into here, okay, and then what you do is you integrate them over all dV, over all the velocities of the electrons. What distribution is that? It's a Maxwell distribution, right? If you integrate over all the velocities, you got a V here that comes into here. The ionization energy, you just replace that with that. And then you've got the V squared dV from here, okay, because that's equal to that. You integrate this over all V. Now this is actually, this integral integrates to just this because you're integrating, you're integrating over the Boltzmann equation, and it has a unity area by definition, the velocity distribution of electrons. So this integral on this side integrates out to unity, and you have a leftover integral on this side, and that you can show by simple substitution of x equals the mass velocity squared over 2kt square root of. If you do that substitution, you get this nice little integral. Everything else pulls out that's a constant, and that integral is square root of pi over 4. Sweet. Okay, so what do you end up with? I'm just going to draw it out for you. N of 1 jk over n of 1, whoops, j plus 1 k over n of 1 jk is equal to 2 over ne times 2 pi mass of electron times kt divided by good old Planck's constant squared, all that to the 3/2 times g of 1 j plus 1 k over g of 1 j k exponent of pi j k over kt. All right. Let's look at this equation for a minute and think about it intuitively, okay? Best way to do this. I just want you to forget about it being the ground state for now. But we're just going to do the simple thing. We're going to assume that we're in a gas where atoms are hanging out in the ground state, whether they're ionized 3 times or 2 times or 1 times. It just makes life simpler to think of it that way. Okay, what this is saying is that, what does it depend upon? This ratio. This ratio. This ratio depends upon the ionization energy of this guy. This is the one getting the electron removed from it, right? So it depends upon the ionization energy of the initial state, or I should say of the less ionized state. So always remember that, okay? You only see one j plus 1 on the right-hand side, and that's the statistical weight over here. But on the right-hand side, everything else is j, the statistical weight of j and the ionization energy of j, because it's the one getting the electron stripped from it. Okay? This is a product of the statistical weight of the free electron pool, and we find out that all we end up depending upon is temperature for all of this, don't we? So we're going to call that phi of j, k of t. Well, plus the 2. So we get 1 over NE times phi of J, K of T. What's interesting is that this J is the index for the lower state and for which you use the ionization energy. Okay? The only J plus 1 is in the statistical weight of the higher ionization stage. Okay? All right. So what do we find out? We found out that we have a temperature dependence and an electron density dependence. And through Emma's question, we answered why the electron density. Because the higher that is, it pushes us to a lower number because you're getting higher rates of recombination relative to the, well, the balance. The rates in and rates out are the same, but the balance is that the recombinations drive you to a lower equilibrium ratio. Okay, because recombination is so common. All right. But as you increase the temperature, what do you find out? That the ionization, that you get more of the ionized. And why? Because when you increase the temperature, you're increasing the velocities of the electrons. Okay? That reduces the probability of recombination. Faster electrons don't combine as easily as slower electrons. They get sucked in easier, just like a slower satellite gets sucked into the planet easier than a fast satellite. It's kind of the same phenomenon, but that's gravity as opposed to electromagnetic. So when you increase the temperature, you're actually driving yourself up. Did I say that backwards? I think I said that backwards. I think I did say that backwards. So that's a negative effect, but the positive effect is that you're increasing the radiation field with the temperature as well, and that's dropping down from the H nu, these T's. So actually I don't have as clean a physical intuition for why when you raise the temperature you actually get this ratio to go up. And the thing is, what part of me knows is that the electrons are moving with higher average speeds, but that reduces your recombination rate. Right, by reducing the recombination rate, you push yourself up to higher ionizing. Okay, so higher electron density, you have a higher propensity of recombination, you lower. With temperature, you increase the speed of your electron pools, and that reduces your recombination rate. It also makes you have higher photon energies, which is higher photoionization, and so the temperature will drive this ratio up. So T goes up, N of 1J plus 1K over N1JK goes up, and vice versa if it goes down, and NE up, and this goes 1J plus 1K over N1JK goes down. Okay. Any other questions about that? So it depends upon NE and T. NE is going to be dependent upon the pressure of your gas, how much pressure it's under. Okay. All right. Now, this is only for the state and state I. Or sorry, this is only ground state ionized to ground state less ionized by one stage. Okay. And this isn't the final phi that I want to write. Okay. But we're going to borrow this notation. And we're going to redefine phi. Maybe, if you will allow me, and I apologize if you could just adjust your notes there, because I don't have it actually written as phi in my notes, but I jumped the gun. Just call that a little phi to designate that it's for the ratio of the ground states. All right? So here's the deal. You want to know not just what the ratio is for the ground states, but you want to know what the ratio is for the first excited states and the second excited states. In fact, you want to know the ratio for all excited states. Okay. So, effectively, all you have to do from realizing that njk is equal to the sum over all states, okay, you can apply that to this equation very simply, and guess what you get? The same equation, except for these get replaced with the partition functions. I'm just going to say that. I'm not going to do the derivation for you. Okay? If you want to see the derivation, go to the typewritten notes. Okay. And now we can write it as 1 over NE capital phi of T. So when we talk about capital phi for the remainder of our notes, we're actually talking about, okay, and then I get rid of the excitation state here. Okay. So what I've done is I've said, hey, you can do this starting with the Boltzmann equation, and you can then integrate the Boltzmann equation over all velocities with the electron field, and you get the ratio in terms of the statistical weights for, say, the ground state or the second state, whatever state you want. But if you want it for all all excitation states, I, then you sum the top and the bottom over the all excitation stages, and equivalently what you're doing is you're replacing the statistical weight of a given excitation state with the partition function. In other words, the statistical weight of the combined all possible excited states. So now we're talking about we're talking about species K, okay, in ionization stage J plus 1 over species K in ionization stage J densities. Okay.
Yeah.
That worked out nice. Okay. Depends upon the electron density, the inverse of the electron density, and depends upon this, if you will, Saha ratio, which is only a function of temperature. The J and the K come in for the species that's in the denominator, because you need to know the ionization potential of the species in the denominator, because that's the more neutral species, the one that's having its electron removed. So you need to contain physics for the energy to remove that electron. And then you have the statistical phase space weight of the electron field as a function of temperature. You have the statistical weight in the denominator for the lower ionization stage, and you have the statistical weight of the partition function for the ion in the higher ionization stage. Again, we apply the two assumptions, thermal equilibrium and detailed balancing. I want to emphasize to you, do not just pull your Saha equation or your Boltzmann equation out of your hat if you're talking about an H2 region or you're talking about an intergalactic filament or something like that. In those cases, the photon field is not in equilibrium with the particle field. It is not in thermal equilibrium. It's a whole nother ball of wax, and I would love to teach a class on that called low density gas physics, which I could teach you all how to model a real gas cloud and not just an approximation of a gas in thermal equilibrium, which is a rare case. Yes, there are regions of stars which are very close to thermal equilibrium, and there are some places, but for the most part, it's a very limited tool that I've provided you today, or that you've picked up wherever you've seen it before. So just want to make sure you understand the limits of its applications. Okay. Now, are there any questions? Okay. So this other page here just gives the Saha equation in terms of the electron pressure and the theta notation, in case you like that better. And it also gives it to you in log notation in terms of electron density, and log notation in terms of electron pressure. You read different books, they write it in different ways. So I've just sort of boxed each one for you so you have it in front of you. Okay? Good to go? Okay. Let's talk about ionization potentials for a minute. This is a table of these numbers. Okay? Ionization energies. Okay? So, if you look on here, chi, capital I, J, K. Element here, and the energy here for the first ionization. So to remove the first electron, that's the energy. To remove the second electron is here, the third one, etc. Okay? And you'll see, for example, let's look at oxygen. To remove the first electron of oxygen is almost the same energy as it is to remove the first electron from hydrogen. So whatever the ionization fractions are of hydrogen, the ionization fractions of oxygen 1 ought to be pretty close. Not perfectly, because you have to account for recombination at different rates because they have different nuclear charges. Okay? But you can see that photoionization or collisional ionization, it happens at about the same temperature. But if you go to oxygen, to remove the second electron takes 35 eV, the next one 54, and the next one 77, and the next one 113, and the next one 138, etc., etc. Okay, so you're getting to high energies. So you have to have very hot gas in order to remove those, to get a number density, a large number density of oxygen 6, for example, you'd have to be in a very hot gas. And it turns out that oxygen is predominantly in the oxygen 6 phase with gas that's around 300,000 degrees. That's pretty damn hot. Okay, you cool the gas off, there's not as much oxygen 6, there's more oxygen 5 and 4. So the number densities of oxygen 5 and 4 will be higher and oxygen 6 will be lower. So you see that the fraction in a given ionization stage changes with temperature. Okay, we're also going to find out it changes with electron number density because of the recombination. This is a chart of those that I made, put in my little book whenever I get around to publishing the damn thing, before I die, I hope. And it shows the dashed line here is the 13.598 eV of hydrogen. So look at the ones that are below the ionization energy of hydrogen. This is a very, very important point I want to make here. In a gas that is cool, okay, almost all of the free electrons come from these particular metals with their low ionization energies. Okay, so if you were in a cool gas, you are prominently going to get electrons from, say, beryllium, sodium, magnesium, aluminum, silicon, potassium, calcium, etc., you know, titanium, chromium, even iron. But they'll be in proportion to their number densities. And so it turns out that, yeah, there's not really, you know, the abundance of beryllium is actually quite low. So, yeah, beryllium doesn't really end up contributing that many electrons. It really turns out that sodium and silicon and aluminum and magnesium and then calcium and chromium and stuff like that. Those are the ones that end up contributing. So you can have a gas which is predominantly neutral in hydrogen, and yet it will still have electrons in it, free electrons in it, and they will come from a certain subset of metals that have their first electron with very low ionization energy. And that's very important. If you have a pure hydrogen and helium gas, you're at low temperature, the only free electrons will be ones that basically come off of hydrogen. Okay? Maybe some helium, but mostly hydrogen because there's so much hydrogen compared to helium. So really the electrons are predominantly all from hydrogen. But now if you put metals in that gas, the number of free electrons is going to go up dramatically, and it's going to be mostly due to all those metals with the very low ionization energies. Okay? So that's why in very cool stars, such as let's say the Sun or a K star, you see a lot of the free electrons, particularly in K stars, come from calcium and iron and sodium and things like that. Okay, it's not until you start getting to an A star where you really start to be dominated by the free electrons in the gas are dominated by the hydrogen. Okay. Okay. Now comes the last piece of information you need to be able to solve the homework problem. Problem 3. Okay. Everybody needs a 7th inning stretch, I can see that. Okay, but this is a very important step. I'm going to erase this if you don't mind.
Yeah.
Ionization fractions. F, J of K. We're going to find out are a function of NE and T. And they are defined as N of JK divided by N of K. N of JK is the number density of species K in ionization stage J. When you sum species K over all of its ionization stages, you get the number density of species K. That's number density conservation. You take the ratio of any ion, the density of any species in stage J, to the total density of species K, you get what's called the ionization fraction. I've introduced it before. What we want to know is how can we calculate those? Okay. Well, we do know how to calculate the ratio between stage J and J plus 1. That's all we know. But we want this. The simplest case is to consider hydrogen. So, straightforward. Basically, hydrogen is N1, and it can exist in 2 ionization stages. Neutral, species 1, and ionized, species 1. And following the sum, it's the sum of the neutrals plus the ionized. Okay? So, what we find out is that F11 is equal to N11 over N1. That's equal to N11 over N11 plus N21. Okay? If you factor out N11, Everybody follow that? A little algebra for you there. But this is basically species K in ionization stage 1 to species 1 in ionization stage 2. Got it? What about F21? Well, the easiest way to do this is to divide the numerator and the denominator by N11. N11 over N11 is 1. N21 over N11. What's the numerator? P11 of T over NE. And what's the denominator? I love the look on your face. Are you kidding me? Really? So with hydrogen, it's pretty straightforward. You ever wonder why so many times you read a paper? I hope so many times you read a paper. But when you read papers that you see that people could calculate the ionization fraction of hydrogen, like, oh yeah, it's equal to blah, 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 blah. They throw in some numbers and bang, they got it. Because hydrogen is very straightforward. So now we have a relationship that N11 is equal to F11 times N1, and N21 is equal to F21 times N1. Where F11 now depends upon temperature and electron number density through the Saha equation. And F21 depends upon temperature and electron density through the same set of Saha equations. Check this out. One over this is F11. So 1 over that and times that. So if you take this and multiply it by F11, you've got F21. Now that's fancy, folks, because why? Because you just got to calculate this ratio once. Right? You take 1 over 1 plus the ratio, you got F11. You take that ratio and multiply it by F11, you got F21, and you are off to the horse races. Okay. Anybody want to do helium? No. Okay. Well, I went ahead and I did helium for you. Okay, it's very similar. Okay. What I'm going to show you is that there's a simple recursion formula. Okay? Very simple. As long as you can calculate 1 over NE phi T, you can just racehorse this stuff and calculate anything. I am going to define phi y of jk as n of j plus 1k over n of jk. Just a new definition, which is equal to 1 over ne phi of jk. That's going to be my definition. Just because using y's just simplifies my notation. Okay? So, according to hydrogen, F11 equals 1 over 1 plus y11. And F12 is equal to y11 over 1 plus y11 equals y11 F11. It's kind of nicer, right? It's kind of easier to swallow.
2-1 for hydrogen.
Thank you. Should be 2-1 for hydrogen. Thank you. Okay. So what happens now is if I'd done helium for you, which is just another extension of this, you would have gotten for helium, okay, this was hydrogen, remember? For helium, K is 2, so F12, you're going to get 1 over 1 plus y 1, 2 plus y 1, 2 y 2, 2. Maybe I should have done helium so you could see how that happened. But anyway, if you go through my notes, which I'm hoping you'll do, I gotta leave something for you guys to study. Okay? If you go through my notes for helium, you'll see how you get an extended denominator. And you get F22 is equal to y22 F12, and you get F32 is equal to y32 F22. Did I get that right? And then, yeah. Okay. So basically, this F12 is basically 1 over this nasty denominator, where each of these y's are given by the NE and T. So this goes as 1 over NE, but this goes 1 over NE squared. Okay. And so basically you take the y22 and multiply it by the denominator. Then this is y22 times the denominator, you multiply it by y32. So in a sense, this is really, y22 over 1 plus y12 plus y2y22. And this is equal to y32 times y22 over 1 plus y12 plus y12 y22. I know it looks nasty, but this is much simpler notation than writing that. In other words, once you calculate this in your code, you can just say F12 times Y22 is F22, then F32 is F22 times Y32. You see what I'm getting?
I think the Y's are, well, they don't match. I guess I haven't gone through the math, whatever you've done, but they don't match what you have in here. You have Y12, Y22.
That's for lithium?
No, for helium? We're doing helium, right?
Right.
That's it.
1, 2 is Y12. Oh, 1, 2, 2, 2. Yeah. 2, 2. F22 is Y.
1, 2.
F12, Y12. That's correct. Thank you for catching that. Right, 2, 1, 1, 1, 1, 1.
Yes.
Yes, this is 1. I was going to get into the rule of thumb. 2, 1, 1, 1, 1, 1. 2, 2, 1, 2, 1, 2. 3, 2, 2, 2, 2, 2. So whatever this is the J1 below it. Okay, F12 is 1 divided by the denominator. 22 is 1, 2 times 1, 2. F32 is 2, 2 times 2, 2. Thank you for catching that. I'm so glad that you are more awake than I am today. Yes, I think we're there. Good catch. So, if you want to ask yourself if you understand the derivation, try it for lithium. Okay. Now, I want to introduce to you now what I consider to be the recursion formula, which is so easy for programming this up. So it just makes programming this up so easy. And I'm pretty happy with this because the first time I saw the recursive formula, I actually saw it in a book by Mihalis in 1970. And the way he writes it is unintelligible. It's a set of ratio of these products of sums and NEs and fees, and it's just crazy. And I taught it that way the first semester. And those poor kids, way back in 2003 or whatever it was, they learned it that way. But over time, I realized you could simplify it into this Y, and you could write it this way, and it's much simpler. And now watch what happens with the recursion formula. Okay. So now you can take any random JK. Okay. And you can say, define capital S of K as the sum of something we're going to call PJK. Okay, let me get this right. No. The sum of all, you're like, wait a minute, you're adding more notation. Just trust me for a second, this is going to make some sense. And the recursion formula is that P of JK is equal to P of J minus 1 K, should be a K there, times Y of J minus 1 K. And the definition is going to be that P of the ground state 1, sorry, of the neutral state is defined as 1. Okay, defining that as 1, okay, and then your F of 1, K, is 1 over SK, and your F of JK is equal to F of J minus 1K times, guess what, Y of J minus 1K. This you already know, right? That you already know because that's what we showed over here. You know, 2, 2 was 1, 2, 1, 2. Okay? 2, 2 was 1, 2, 1, 2. So you just have to calculate the y's, which is easy to do because all you need to know is your J and your K, your partition functions, and your ionization energy, and your electron density. Bam, you get Y. Okay, so you have all of these. Okay, so now that you've got all these, you say, sum up these PJKs. When J equals 1, it's equal to 1. Okay, when J equals to 2, it's P of 1 and Y of 1. And you add that to when J equals 3 of P of 2, Y of 2. So it's very simple. What do? You calculate 1. You compute, I'm doing this off the fly, Y of JK for all JK. Okay? That's one way to think of doing it. Okay? And then you compute S of k, by saying, okay, I start out with 1, in this case, S of k is going to equal P1 plus P1k plus P2k plus P3k dot. P1k is 1 plus 1 times P of 1k y 1k P of 1k is 1 plus y of 1k plus P of 3 is going to be it ends up being y 1k times y of 2k, right? The next one, P3 is 2k, right? Plus P of 4k is y 1k times y of 2k times y of 3k. Because it's equal to this times 3k. See, that's P3k times y3k. Etc., etc. 1k times y, 2k. Dot. So 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. That formula gives you this. And that is your denominator. So once you compute Sk, you compute f of 1k is equal to 1 over Sk. Okay? So you now have f1k. So f2k is f1k times y1k. f3k is y2k times, or f2k times y2k. You've got them all. You've already calculated them all. And so you just go right up the chain of all your ionization fractions. I hope I've not made it more complicated than it really is.
So what is
So why are we doing this?
SK? What in a sentence? What is SK?
SK.
What is that number?
Sk is the denominator of all your ionization fractions. Okay? It is the denominator of all your ionization fractions. And what it turns out to be is this kind of running sum product. Okay, it's a sum where the product continues to get larger and larger. Okay, 1 plus y1k plus y1k times y2k plus, and this is, why is this? Because let's not forget what these are. What is each one of these? Right? yjk is y of j plus 1k over jk. So this is in 2k over in 1k. You can calculate that. That's why we have, what's 1k times 2k? Well, this is n2k over n1k times n3k over n2k. What is that really equal to? That is really equal to n3k over n1k. But you've done it in 2 parts. Okay, you've done this in 2 parts because you can only get the adjacent ratios. So what you're doing is you got first the ratio of 2 to 1, then you got the ratio of 3 to 1, but you had to do it in 2 parts. This is the ratio of 4 to 1, but it has to be done in ratio units of 2 to 1, 3 to 2, and 4 to 3. but ends up giving you 4 to 1. Maybe it would have made more sense if I'd done helium. If I'd done the derivation of helium, we would have seen it better, I think. I should have done the derivation of helium.
So it's sort of like a unitless total for.
Okay, let's look at it. What's the ionization fraction? Right? Is everybody with me on that? I guess I'll go ahead and sort of derive it from this formula for you. Fjk is equal to njk over nk. Nk is the sum of njk, which is n1k plus n2k plus n3k plus n4k up to k plus 1. So what you're doing here is you're saying, let's factor out n1jk over n1k, n1k over n1k plus n2k over n1k plus n3k over n1k plus n4k over n1k, dot, 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 dot. Okay? We can't get j to 1 directly if j happens to be 5. So we write the numerator as njk over nj minus 1k times nj minus 1k over nj minus 2k, dot, 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 until we get to n of 2 over n of 1. These are all your y's multiplied together. Over here, this is 1 plus n2k over n1k. We can do that. That's just y of 1, 1, or 1k. Plus, how do we get this? This is going to be n3k over n1k. Well, we can't do that, but we can calculate n3 over n2 times n2 over n3. Because those are adjacents, that's y 2 or 2k. This is y of 3k. And when we get to this one, this is n3, this is a 4. Right? n4 of k, that's n4 of k over, well, we can't do n4 over n1. We don't have a formula for that. But we can do adjacents. So we do the same trick. n3k over n2k times n2k over n1k. Right? Folks, that's y11. What's y1k? This is y1k times y2k. This is y1k times y2k times y3k. Of course, I got them backwards. This is the 3k, this is the 2k, that's the 1k. So that's where the denominator comes from. And the numerator, the reason you get this product here is because you keep, every time you go up to another ionization stage J, you're adding another one of these. When you start at 1, you're here. Well, when you start at 1, this is 1. When you go to 2, you're here. When you go to 3, you include this term and this term. When you go to J minus 1, you include all those terms when you go to J. So you keep adding, or you keep producting one more of these terms. Does that help? Did that help? I'm getting a nod to the affirmative. All right. So that's the general derivation to show you that if you calculate all the y's from here, and then you calculate your P's, and you sum up your P's, and then you're off and running. Now, what do you need to know to do this? You need to know N sub E and T. All right. Bear with me, I know it's time to go. Now, you're not going to do this on this homework assignment. You're going to apply this equation for iron on this homework assignment, but you're going to know Ne and you're going to know T. I give them to you. And you're going to know the partition functions. I give them to you. Your job is to just execute this for 3 stages of iron. That's what problem 3 is. So I'm giving this to you. Your problem sets are sort of piecemeal. Can you look at the equations and apply them, given all the information? Later on, you're going to be given P and T. From that, you're going to calculate N total. Remember that N total is the nuclear plus the electron. Okay. This is constrained by that, but you don't know these. How do you get Ne? Now, have you soiled your diapers? Do you understand what that means? I have to calculate all my FJK, but to do that I have to know Ne and T. Well, I'm going to give you T. But to get Ne, I got to solve this equation, which has Ne appearing in it. In the ionization fractions themselves are a function of Ne, and I have to know Ne to calculate this to solve for it. That's what you call iterative algorithms. That means I'm going to throw at you this, and I'll give you the alpha k's, from which every time you iterate to solve this equation, you have to recalculate all of that. That's going to be the next homework assignment. So enjoy this one, because it's very, very simple. It's straightforward. But the point of this one is you're going to have now exercised your ability to use these equations so that you can now plug them in to solve for this. Once you know how to do this, you are kings and queens. And I can throw at you an atmosphere where the pressure now is, or temperature and pressure are going to change in each layer, and then you're going to, we're getting there, folks. We're getting there. Leave a little faith. I know. Enjoy.